To measure the kilowatt-hour consumption of a subpanel, there are two primary methods. Firstly, submetering with a current transformer, or CT, and secondly, submetering with a split-core current transformer, or SCCT. Let's look at each in detail. With the current transformer method, you install a current transformer on the main feeder cable supplying the subpanel. Connect the CT to a meter that measures the current flowing through the feeder. The meter calculates the kilowatt-hour consumption by integrating the current over time. With the split-core current transformer method, you install a split-core current transformer around the main feeder cable supplying the subpanel. Connect the SCCT to a meter that measures the current flowing through the feeder. The meter calculates the kilowatt-hour consumption by integrating the current over time. Now let's look at specific devices useful for submetering. Current transformer meters are designed to be used with CT and can measure current in high-voltage applications. Split-core current transformer meters can be easily installed around existing electrical cables without cutting the conductors. Some data loggers have built-in current measurement capabilities and can be used for submetering applications. When installing a submetering system, there are several important considerations. The CT or SCCT must be sized appropriately for the current flowing through the feeder cable. The meter must be calibrated to ensure accuracy. The installation must comply with local electrical codes and standards. There are several benefits to submetering. It allows you to monitor the energy consumption of the subpanel separately. It facilitates accurate billing and cost allocation. It provides data for energy efficiency analysis. To elaborate on current transformers, these are essential components in submetering systems, playing a critical role in accurately measuring the current flowing through electrical conductors. They work on the principle of electromagnetic induction, where the current in one circuit induces a current in another circuit. A current transformer typically consists of a core made of ferromagnetic material, around which two windings are wrapped: the primary winding and the secondary winding. The primary winding is connected in series with a conductor whose current is to be measured, while the secondary winding is connected to a meter or other measuring device. When current flows through the primary winding, it creates a magnetic field in the core, which in turn induces a current in the secondary winding. The ratio of the primary current to the secondary current is determined by the turns ratio of the transformer. For example, a current transformer with a turns ratio of 100:1 will produce a secondary current that is 1/100th of the primary current. This allows the meter to measure the current without being directly exposed to the high voltage of the primary circuit. Current transformers are available in a variety of sizes and current ranges to accommodate different applications. They are also available in different types, such as window-type current transformers, which have a window through which the conductor passes, and split-core current transformers, which can be opened and closed around the conductor without disconnecting it. Selecting the right current transformer for a particular application is important to ensure accurate measurements. The current transformer should be sized appropriately for the current flowing through the conductor, and it should have an accuracy rating that meets the requirements of the application. Proper installation and maintenance of current transformers are also essential to ensure their continued accuracy and reliability. Split-core current transformers offer a significant advantage over traditional current transformers in that they can be installed without disconnecting the conductor. This makes them ideal for retrofitting existing electrical systems or for applications where downtime is not an option. A split-core current transformer consists of two halves that can be opened and closed around the conductor. The two halves are typically held together by a hinge or latch. When the two halves are closed, they form a complete magnetic core around the conductor. Like traditional current transformers, split-core current transformers work on the principle of electromagnetic induction. When current flows through the conductor, it creates a magnetic field in the core, which in turn induces a current in the secondary winding. The secondary winding is connected to a meter or other measuring device. Split-core current transformers are available in a variety of sizes and current ranges to accommodate different applications. They are also available in different types, such as hinge split-core current transformers and latching split-core current transformers. Selecting the right split-core current transformer for a particular application is important to ensure accurate measurements. The split-core current transformer should be sized appropriately for the current flowing through the conductor, and it should have an accuracy rating that meets the requirements of the application. Proper installation and maintenance of split-core current transformers are also essential to ensure their continued accuracy and reliability. Data loggers are electronic devices that record data over time. They are often used in submetering applications to collect and store data on energy consumption. Data loggers typically consist of a sensor, a data storage unit, and a communication interface. The sensor measures the electrical current, voltage, or power. The data storage unit stores the data. The communication interface allows the data to be downloaded to a computer for analysis. Data loggers are available in a variety of sizes and types to accommodate different applications. They can be battery-powered or line-powered, and they can store data for days, weeks, or even months. Some data loggers have built-in displays that show the current readings, while others require a computer to view the data. Selecting the right data logger for a particular application is important to ensure accurate and reliable data collection. The data logger should be selected based on the type of data to be collected, the accuracy required, the storage capacity needed, and the communication interface desired. Proper installation and maintenance of data loggers are also essential to ensure their continued accuracy and reliability. When selecting a meter for submetering, it's essential to consider several key factors to ensure accurate and reliable energy monitoring. Firstly, the meter's accuracy is paramount. Look for meters with a high accuracy class, typically expressed as a percentage, such as plus or minus 0.5% or better. This indicates the maximum deviation from the true value that the meter is allowed. Secondly, consider the meter's voltage and current rating. Ensure that the meter's voltage and current ratings are appropriate for the subpanel's electrical system. The meter should be able to handle the maximum voltage and current that the subpanel is likely to experience. Thirdly, evaluate the meter's communication capabilities. Some meters offer communication interfaces such as Modbus, BOSSnet, or Ethernet, which allow them to be integrated into building automation systems or energy management platforms. This enables remote monitoring and data collection. Fourthly, assess the meter's display and user interface. A clear and easy-to-read display can simplify on-site monitoring and troubleshooting. A user-friendly interface can make it easier to configure the meter and access historical data. Fifthly, ensure that the meter complies with relevant industry standards and certifications such as ANSI 12.20 for electricity meters. Compliance with these standards ensures that the meter meets certain performance and safety requirements. Sixthly, consider the meter's power quality monitoring capabilities. Some meters can measure power quality parameters such as voltage harmonics, current harmonics, and power factor. This can be helpful for identifying and addressing power quality issues in the subpanel's electrical system. Seventhly, evaluate the meter's data logging capabilities. A meter with built-in data logging can store historical energy consumption data, which can be used for energy analysis and identifying opportunities for energy savings. Eighthly, consider the meter's cost. Meters vary in price depending on their features and capabilities. Choose a meter that meets your requirements and fits within your budget. Ninthly, select a meter for a reputable manufacturer. Reputable manufacturers typically offer reliable products, good customer support, and warranties. Tenthly, consider the meter's installation requirements. Some meters are easier to install than others. Choose a meter that can be easily installed in the subpanel's electrical system. Choosing the right meter for submetering requires careful consideration of these factors. By selecting a meter that meets your specific needs and requirements, you can ensure accurate and reliable energy monitoring, which can help you save energy and reduce costs. For current transformers, it's crucial to select the appropriate size to ensure accurate current measurement and prevent damage to the transformer or the electrical system. The size of a current transformer is determined by its current rating, which is the maximum current that the transformer can safely measure. To select the right size current transformer, you need to know the maximum current that the conductor will carry. This can be determined by calculating the load on the circuit or by measuring the current with an ammeter. Once you know the maximum current, you can select a current transformer with a current rating that is equal to or greater than the maximum current. It's important to choose a current transformer with a current rating that is not too much higher than the maximum current. If the current transformer is too large, it will not be as accurate, and it may not be able to measure small currents. In addition to the current rating, you also need to consider the burden rating of the current transformer. The burden rating is the maximum impedance that the secondary winding of the current transformer can drive without affecting the accuracy of the transformer. The burden rating of the current transformer should be greater than or equal to the impedance of the meter or other device that is connected to the secondary winding. If the burden rating of the current transformer is too low, the accuracy of the transformer will be affected. Finally, it's important to choose a current transformer that is suitable for the environment in which it will be used. Current transformers are available in a variety of enclosures to protect them from moisture, dust, and other contaminants. Proper sizing of current transformers is essential for accurate current measurement and to prevent damage to the transformer or the electrical system. Be sure to consider the current rating, burden rating, and environmental conditions when selecting a current transformer. Calibration of a submeter is a critical step in ensuring its accuracy and reliability in measuring energy consumption. Calibration involves comparing the meter's readings to a known standard and adjusting the meter if necessary to ensure that it is measuring accurately. There are several reasons why calibration is important. Firstly, meters can drift over time due to changes in temperature, humidity, and other environmental factors. Calibration corrects for this drift and ensures that the meter is measuring accurately. Secondly, meters may not be perfectly accurate when they are first manufactured. Calibration verifies the meter's accuracy and corrects for any manufacturing defects. Thirdly, calibration ensures that the meter is measuring energy consumption in accordance with industry standards. Calibration is typically performed by a qualified technician using specialized equipment. The technician will connect the meter to a known standard, such as a calibrated power source, and compare the meter's readings to the standard. If the meter's readings are not within the specified accuracy range, the technician will adjust the meter until it is measuring accurately. The frequency of calibration depends on the type of meter, the application, and the manufacturer's recommendations. In general, meters should be calibrated at least once a year, or more frequently if they are used in critical applications. Proper calibration is essential for ensuring the accuracy and reliability of submeters. Calibration ensures that the meter is measuring energy consumption accurately in accordance with industry standards, and that it is providing reliable data for energy management and billing purposes. Electrical codes and standards play a crucial role in ensuring the safe and reliable installation and operation of electrical systems, including submetering systems. These codes and standards provide guidelines and requirements for various aspects of electrical installations, such as wiring methods, overcurrent protection, grounding, and equipment installation. Compliance with electrical codes and standards is essential for several reasons. Firstly, it protects people and property from electrical hazards, such as electric shock and fire. Secondly, it ensures that electrical systems are installed and operated in a safe and reliable manner. Thirdly, it provides a common set of rules and guidelines for electrical installations, which helps to ensure consistency and compatibility. The most widely used electrical code in the United States is the National Electrical Code, or NEC, which is published by the National Fire Protection Association, or NFPA. The NEC is updated every 3 years and provides comprehensive requirements for electrical installations. In addition to the NEC, there may be local electrical codes and standards that must be followed. These local codes and standards may be more stringent than the NEC in some areas. When installing a submetering system, it's important to consult with a qualified electrician or electrical engineer to ensure that the installation complies with all applicable electrical codes and standards. The electrician or electrical engineer can help you select the right equipment, install it properly, and ensure that the system is safe and reliable. Compliance with electrical codes and standards is essential for ensuring the safe and reliable operation of submetering system. By following these codes and standards, you can protect people and property from electrical hazards and ensure that the system is installed and operated in a safe and reliable manner. There are several key benefits to implementing a submetering system. Firstly, submetering enables accurate billing and cost allocation. By installing submeters in individual units or departments, you can accurately measure their energy consumption and bill them accordingly. This eliminates the need for estimations or approximations, which can lead to disputes and inaccuracies. Secondly, submetering promotes energy conservation. When tenants or departments are responsible for their own energy consumption, they are more likely to be mindful of their energy usage and take steps to conserve energy. This can lead to significant reductions in energy consumption and costs. Thirdly, submetering provides valuable data for energy management. By collecting data on energy consumption patterns, you can identify areas where energy is being wasted and implement strategies to improve energy efficiency. This can include upgrading equipment, improving installation, and implementing energy-saving policies. Fourthly, submetering can improve tenant satisfaction. When tenants are billed fairly for their energy consumption, they are more likely to be satisfied with their landlord. This can lead to improved tenant retention and reduced vacancy rates. Fifthly, submetering can increase property value. Properties with submetering systems are often more attractive to tenants and buyers, which can increase their value. Sixthly, submetering can help you comply with local energy efficiency regulations. Some jurisdictions require submetering in certain types of buildings. By installing a submetering system, you can ensure that you are in compliance with these regulations. Seventhly, submetering can provide a return on investment. The cost of installing a submetering system can be offset by the savings in energy costs. In many cases, a submetering system can pay for itself in a few years. Overall, submetering offers a wide range of benefits, including accurate billing, energy conservation, improved energy management, tenant satisfaction, increased property value, compliance with regulations, and a return on investment. When choosing a submetering system, it's important to consider the specific needs of your property and select a system that meets those needs. The specific type of panel board mentioned earlier is not a major detail within the answer. The NEC, or National Electrical Code, Article 220 deals with branch circuit, feeder, and service calculations. Article 220 provides guidelines for calculating the minimum size of branch circuits, feeders, and services for various types of loads, including lighting, receptacles, and appliances. This calculation ensures that the electrical system has sufficient capacity to handle expected loads without overloading. The information regarding NEC Article 220 is for calculation of the loads.